let's start off with the first problem, which is localization. My first problem for today. Now, it turns out I already have a sensor that gives me location. So why do I need another way to solve that up? That's the same sensor that you use when you travel with your mobile phones like this. And the sensor is, of course, called as a GPS. So it gives you the position. So why do I need anything more? By the way, if you're using satellite navigation like this, it uses much more than the GPS. It also has an accelerometer, so you know how much the mobile phone is accelerating at the different axes. It could be used to have an indicative idea of the position as well. So that's my GPS. Now the problem is the GPS error is a few meters. So let's say 5 to 10 meters. It could go up to 15 meters as well. There are concrete buildings where satellite signals cannot navigate and therefore the errors are much large. So indoor, I actually cannot use a GPS because indoor, if you look at outside my office, the entire space is just a few meters. So, in fact, this entire office is less than 6 by 5 by 5 meters, and it's one of the biggest offices of this institution. So, I cannot operate with such a high error. Now, you can always make in your local GPS. How does a GPS work? You've got satellite 1, you've got satellite 2, and you've got satellite 3. And you do the triangulation, so you know the amplitude, so you know the approximate radius, and where these two intersect is right here is approximately your position. Now instead of satellite, I can always use a Wi-Fi, and I've got my position over here, but then again the problem is that the error is a few meters. In actual robotics right now, we're not dealing with swarm robotics. We talk about millimeters of errors in the indoor scenario and centimeters in the outdoor scenario. So this has a problem, and that's why we say that it can do global localization only. Which is, it can overall give you a position, but it cannot tell you precisely where you are. Or in the previous example over here, you will see that the dot moves, but then the dot moves haywire. So sometimes it can also be on the obstacle because of this. I need to know exactly how much of distance do I have with the obstacles. Otherwise, I cannot apply my potential field. I cannot apply my vector field histogram unless I have expensive onboard sensors, and therefore let us improve the localization. So now I'll give you two ways by which I can localize. The first way to localize is that's my autonomous mobile robot. These are the two wheels. It moves by a differential of the two wheels. Let's draw a bigger picture of what this wheel looks like. So this wheel looks like something like this, exactly as you would expect it. So that's a big circle, and this is where the axle is on which the wheel rotates. Now what I do over here is that I place in another instrument that's called as the encoders, and it has spikes. And what I do over here is that behind this circle, I place a receiver, and in front of this, I place a transmitter. And as the wheel turns, that's what happens. So that's my transmitter, that's my receiver, That's my wheel, and this is my encoder. So as the wheel turns, I get in electrical pulses, I get in electrical spikes. So I can receive, cannot receive, cannot receive, can receive, cannot receive, cannot receive, can receive, cannot receive, can receive, cannot receive, and so on. I get in signals like this. And by counting the signals, I know approximately how much the wheel has turned, and that's a good way to localize. So I know how much the left wheel has turned, I know how much the right wheel has turned, I can calculate the speed of the left wheel, I can calculate the speed of the right wheel, and there's a direct formula to be discussed in robotic intensive courses, not a part of the simulation course, which tells you exactly how much the agent has moved, how much the vehicle has moved, how much the mobile robot has moved. So I know approximately my position. And this way of calculating position is also called as localization using odometry or using motion models. And the word motion model means that my position at time t plus 1, which is basically my x at time t plus 1, my y at time t plus 1, and my angle at time t plus 1, is some function of my position at time t. A control signal ut is applied, which is usually v and omega, for 1 unit of time. And I say that this can be guessed from relevant sensors. Encoders are one of them. Now the problem with encoders is sometimes there is the wheels skid and they don't rotate. So the encoders say the robot is stationary while the robot just drifted, it just skid. These are specifically called as the incremental encoders. This is not the one where you use with the manipulators. With the manipulators, we use the absolute encoder. So that's a manipulator. And this is a same motor that is over here. Take it like the same wheel over here. And there also there is an encoder. So let me draw a bigger picture over here. So this is what it looks like. So this is a capacitor, inductor, or whatever property, electrical or electromagnetic property you want to use, that is behind. And there's one which is on the wheel. So as the wheel rotates, this moves, but this does not move. This is stationary. And with enough electronics and electrical background, you will know that the electrical properties, they change because of a change in distance, and that can be used to measure the absolute position. You can also get it with the normal encoders, that is when you have encoders of different widths. So you can actually measure for how long did you not receive the signal, and that can be used to have an absolute position of the wheel. Okay, bad diagram. So there I draw all the spikes of the same width, and that was the incremental, and in the non-incremental they are of unequal width. So you're not counting, you're basically trying to measure the length of the spike over here, and by measuring the length of the spike you're trying to calculate what exactly is the position. You know at what speed the motor is rotating. You are controlling that approximately. So that's with the encoders. There's another sensor which does exactly the same thing, that's called as the IMU, or the inertial measurement unit. Now it has three sensors inside it. It has a 3-axis accelerometer. So I know the acceleration across all the 3 axes, and double integral of acceleration is actually the position. Now the problem is the accelerometer is placed on this device over here. So as long as I'm only moving orthogonally, then I can double integrate the acceleration, I can get my position, but sometimes I also turn like this. So acceleration in this axis means moving in the y-axis, and after I rotated the same motion in the same direction, the accelerometer is right here, is moving in the x-axis. So I need to know my orientation as well. There are two devices that do that. One is a 3-axis gyroscope. So there's a spinning ball right inside this, and the spinning ball is inside a rigid frame which is attached to the body of the robot or the phone in this example. And as soon as I turn, the body would like to conserve the angular momentum as per the physics principles, and therefore the ball inside will turn in the other direction. And that's the thing that I'll physically measure and report the angular speed at the 3 axes. So I know acceleration across the 3 axes, I know the angular speed across 3 axes. You can also use a magnetometer, just because aeroplanes and ships have been using it for centuries for their navigation. So it's a magnet, so it always points in the north-south direction of the Earth's poles, and I can use it to measure any kind of orientation across the 3 axes. So I can get position by integrating acceleration, I mean, of course, technically I'm trying to compute v and omega and use the same physics formulas using these 3 sensors. And that's another example of calculating position using odometry or the motion models. Now the problem is that in either encoders or in IMU, what I'm doing is that I am integrating something in order to calculate my position. So let's take encoder. Encoder, I'm counting 1, 2, 3, 4, 5. The robot skids a little, I've got some error. I'm calculating 6, 7, 8. The robot skids a little more, I've got some more error. So my position is count of encoder readings plus distance skid. And this only increases with time. And practically what that means is when we use encoders practically with our indoor robots, we make sure the wheels are extremely high quality rubber, that they don't skid at all. So the rubber quality has to be extremely good so that there's absolutely no skidding. And this resolution needs to be extremely high. So I've just drawn a few spikes over here. What I can actually do is that I can draw another spikes over here for a finer measurement. And these spikes need to be extremely large in number so that my approximation errors, they also, because of a low resolution, they also end up increasing errors along with time. So basically this can be summarized as the integral of encoder readings plus noise, which means it is integral of encoder readings plus integral of noise. And this quantity, depending upon the robot, the tire quality, the resolution of the encoders, can become a few meters in a few minutes. So I accurately know my position only for the first 5 to 7 minutes of the run. After that, it's worse than my indoor GPS using Wi-Fi signals. So for the first few minutes, it's extremely reliable. After that, it's useless. Same thing around over here. I'm integrating IMU readings plus noise. So it's IMU readings plus integral of noise. So this becomes too large.